Hello everyone. So in this pre-lecture tutorial, we're going to demonstrate how to do equilibrium constant calculations and pH calculations for weak bases as opposed to weak acids, which were the subject of the previous pre-lecture tutorial. And as you might imagine, the procedure by which we carry out these calculations for bases would be very similar to the procedure that we use to calculate equilibrium constants and pH values for weak acids, though obviously there are some differences which I'll illustrate in this tutorial. So here we have an example problem on the screen, and we have a base, and this base is hydrazine, okay, and it has a pH of 10.7 when it exists as a 0.15 molar solution, and they're asking us to calculate the Kb, where again Kb is analogous to Ka for weak acids. Basically, Kb is what we refer to as the base dissociation constant. And so the best place to start is to actually write a chemical reaction equation that shows the behavior of hydrazine as a weak base. So here we have the formula of hydrazine, and we have it in aqueous solution. It's going to interact with water. Again, being a weak base, we should expect an equilibrium process, and hydrazine, acting as a base, will accept a proton. So we will get this species in aqueous solution and hydroxide ion. And so if we're going to write an expression for this base dissociation, then basically it would be the conjugate acid of hydrazine multiplied by the hydroxide ion divided by the concentration of the hydrazine itself. Now, again, the important thing to understand here is we have a pH value, but if I were to go and calculate a concentration directly off of this pH value, that would actually give me the hydrogen ion concentration, and that does not exist in this particular reaction equation. What I'm going to need to do is convert this pH to a pOH. And if you remember, pH plus pOH is equal to 14, again assuming that we're at 25 degrees Celsius. And again, unless we're told otherwise, then we can make that assumption. And so if I go and solve for pOH here, I would take 14, subtract the pH from it, so that's 14 minus 10.7. So that means my pOH for this particular solution is 3.3. So with this in hand, I can actually calculate the hydroxide ion concentration by raising 10 to the negative pOH power, or 10 to the negative 3.30. If I do that math, I get 5.0 times 10 to the negative fourth molar. And so if I go ahead and construct an ice table, let me rewrite my equation here so that I can create an ice table properly. Okay, filling in the states of matter. So what we have, according to the problem, is an initial concentration of 0.15 molar in the hydrazine. Now again, water being a pure liquid, we would not monitor its concentration within the ice table. Then initially we would have none of the conjugate acid of hydrazine and also none of the hydroxide ion. But I know, based on the pH measurement, again if you recall from our last tutorial, this is actually an equilibrium measurement. Then based on the calculation I carried out earlier, I do know the equilibrium concentration of the hydroxide ion. So that would be 5 times 10 to the negative fourth. So that means that the change for the hydroxide ion was plus 5 times 10 to the negative fourth. Since the stoichiometry is 1-to-1 across the board for this reaction, then basically that means that the change for the conjugate acid of hydrazine would also be plus 5 times 10 to the negative 4. For the hydrazine itself, since that's on the reactant side of the equilibrium equation, then I would be losing 5.0 times 10 to the negative fourth. So if I go ahead and do my arithmetic vertically here for the remaining columns of my table, then that means that my equilibrium concentration of my conjugate acid of hydrazine is also 5 times 10 to the negative fourth molar. And if I do the math for the hydrazine, then that's 1.495 times 10 to the negative first power molar for the hydrazine. Now I have all of my equilibrium concentrations that I would need, and so plugging that in to my equation for the base dissociation constant, that would be 5 times 10 to the negative fourth times 5 times 10 to the negative fourth, and we're going to divide by 1.495 times 10 to the negative first. And if I do that math, then I get a Kb value of 1.7 times 10 to the negative 6. Okay, now as we demonstrated in the weak acid tutorial prior to this one, it's also sometimes customary to be asked to determine a pH for a weak base solution given a Kb value. And so we have this example here where we're dealing with ammonia. Now, again, if we consider ammonia's behavior in aqueous solution, then since it would be a weak base, it would accept a proton, and I would get the ammonium ion as the conjugate acid and the hydroxide ion. And so, again, I'd have to construct an ice table. And again, writing the base dissociation constant based on the law of mass action, I would need to multiply the concentration of the ammonium ion by the concentration of the hydroxide ion, and then divide that through by the concentration of the ammonia. And so I'll go ahead and set up my ice table once again. I have enough quantity of ammonia, 0.75 moles, to make half a liter of solution. And so if I'm going to calculate the molarity, I would need to divide 0.75 moles by a half liter. And so if I go ahead and do that math, that ends up being 1.5 molar in ammonia as the initial concentration. So I have 1.5 molar ammonia, and initially none of the ammonium and none of the hydroxide ion. Again, at this point the change would be unknown, but since I don't have any ammonium or hydroxide, then by Le Chatelier's principle, this equilibrium should move to the right, which means that I should get an increase in ammonium and hydroxide. So each of those equilibrium concentrations of ammonium and hydroxide would be X, and then I would be losing X from the 1.5 molar of the ammonia for an equilibrium expression of that ammonia concentration at equilibrium of 1.5 minus X. And so I would go and plug that in to my expression for Kb. And so that would be X times X over 1.5 minus X is equal to, and I'd set it equal to the value I was given for the Kb. So that's 1.8 times 10 to the negative fifth. Cleaning this up with a little algebra, I get X squared divided by 1.5 minus X is equal to 1.8 times 10 to the negative fifth. Again, based on the small value of the Kb, then we can assume that X is very small, so that in this difference term, 1.5 minus X is very close to just 1.5. And then I would just go ahead and do the algebra. X squared would then be the product of 1.5 times 1.8 times 10 to the negative 5, which is 2.7 times 10 to the negative 5. and then taking the square root on both sides, that gives me x is equal to 5.2 times 10 to the negative third molar. I'm going to quickly check my percent ionization to make sure that this assumption is valid. I would take 5.2 times 10 to the negative third, and I'm going to divide that by 1.5, multiply by 100, and this time I get a percent ionization of 0.35%, which again is less than 5%, which is our limit to consider this assumption valid. And so this assumption is indeed valid, which means I can consider this to be the hydroxide ion concentration. But I was asked for the pH. And so what I would need to do is make use of the relationship that pH is equal to 14 minus POH, or pH is equal to 14 minus the negative log of the hydroxide ion concentration. Right? These negative signs would actually multiply against each other to give me 14 plus the log of the hydroxide ion concentration. So plugging in the numbers that I have, that's 14 plus the log of 5.2 times 10 to the negative third. And so if I do that math, I end up with a pH of 11.72. Okay, so once again, just like we did with the weak acid tutorial, there's a follow-up assignment that's attached to this pre-lecture tutorial video. Go ahead and give it a try. Again, we'll continue to reinforce and work on our application activities related to these calculations. Again, if you have any questions, by all means, let me know. But I will see you guys in class. Have a good night.